Hello class, today I want to go over the rocks lab. You'll need to download the lab here that I've posted for you. It's a fillable lab, so you can do much of it online. And then in terms of the rock samples we'll be identifying, you'll have to come back to our Canvas assignment page here and click on these links to identify these rocks. And I'll go through a few of them with you just to kind of get you going here. And also this lab, I've taken parts of it from a lab book that has their own pre-lab video, so you can kind of watch this and see how they kind of go through their explanation of the lab. But you'll see that much of what they do I'm going to show you how to do right now in this video here. So I've already downloaded the lab, so we'll take a look here at our PDF, which is fillable. So you make sure you put your name up here. And so for this first part on the rock cycle, you'll need to make sure you go over to our video lectures, and I do have them here. And so this first video lecture was presented in the first week's module on minerals, but the latter part of this, really beginning at about 11:27 minute mark here, starts on the rock cycle, right, which completes this here. And so you can see that I give you all the pieces, all the information for that rock cycle in this video lecture. And so like igneous rock, sediment, which is a loose material like sand on the beach. Then you get sedimentary rock. This should be metamorphic rock. And then if you get metamorphic rock too hot, it's going to melt too. And if you have a melt, you're going to make magma again, right? So that's kind of one path in this rock cycle. And so those are the kind of the square boxes. You'll see that on this diagram, they're going to want you to also fill out these bubbles here, which are processes, right? So in order to go from magma to an igneous rock, the magma has to cool and solidify, has to crystallize, right? And they kind of talk about that up in here. And so in order to go from igneous rock to a loose material, because you have to weather it and break it apart, so that's a weathering and transportation aspect here, then you'd get sediment, loose material. And then that's going to eventually going to produce sedimentary rock over here. So what process must involve to go from loose material into making a sedimentary rock? And then just follow that video lecture that I have, and you can fill out these other parts of the rock cycle. And then there's a few questions you'll have to answer about these. Then for activity 2.2 here, we're dealing with igneous rock textures. Remember that igneous rocks are based on two characteristics: texture, basically the grain size, what the rock looks like, and composition, which is the chemistry. So this first part deals with texture. Remember that I give you three fundamental textures. There's phaneritic, aphanitic, and porphyritic, right? Then we have special textures like volcanic, vesicular, or glassy. In fact, you can see the textural terms are drawn in here. Phaneritic, aphanitic, porphyritic. A special texture for obsidian is glassy. A special texture for vesicular basalt, often called scoria, is vesicles or vesicular. And then pyroclastic is fire broken. Remember, clastic means broken in Greek. And so this is magma that's erupted or exploded out of the volcano. And so that expanding gas shatters the magma to make this fire broken fragmental or pyroclastic rock. And often that rock is a volcanic tuff composed mostly of ash, right? It's mostly small fragments here, 4 millimeters here. Or you can get these volcanic breccias. And the general term we use for anything that explodes out of the volcano, that's called tephra. And so tephra is the general class for these pyroclastic rocks. But again, pyroclastic would be our textural term. Before we do composition, let's go back up here and look at some of these textures they want you to do. So you'll look at these pictures to find what type of texture they have, like which samples exhibit porphyritic texture. So definitely sample G here, because that's the two different sizes, and to some extent sample B. And so recall that you can have porphyritic textures in volcanic rocks. In fact, most volcanic rocks will have some minerals in them, but then a matrix of fine-grained material, right? So that's the two-stage history. Remember, the minerals that you can see are called phenocrysts, right? And then the matrix is that background. I often call this a chocolate chip cookie model, where you got the dough and the chips, right? So the phenocrysts and the matrix. Porphyritic texture can also happen in plutonic rocks, like this granitic rock right here, where we have much larger potassium feldspar here. and then smaller background of other minerals. But note that the background, the matrix in this case, is visible. It's phaneritic. I can see crystals there. And then I see much larger orthoclase or potassium feldspar crystals here. So this would also be considered porphyritic, right? So anyways, you can answer these questions based on those pictures there. Then we started looking at composition here. So remember, for composition, we're looking at felsic, intermediate, mafic, or ultramafic. And again, I talk about these in my video lectures. Remember, mafic stands for magnesium and iron, so it's rich in magnesium and iron, whereas ultra is very rich in magnesium. So usually ultramafic rocks are mantle rocks, right? Peridotite. Now, remember, peridotite, I always have an important saying about peridotite. It's important for two reasons, right? It's a rock of the upper mantle, and it partially melts to make mafic magmas, basaltic magmas, right? So note that they don't really put any volcanic equivalent to an ultramafic rock, because rhyolite, andesite, and basalt, all these are volcanic rocks, but they don't have a name for the volcanic ultramafic rock. And so the only way you can get a ultramafic volcanic rock is if you melt the mantle 100%. Melt this 100% to make a lava out of it, right? And Earth is just not that hot enough. You would need temperatures of around 2400 degrees centigrade. Remember, the mantle, the upper mantle where most of these magmas are being produced, is around 1200, 1250. So nowhere near those temperatures to completely 100% melt the mantle. So you would get a partial melt. So when you partially melt peridotite, the mantle rock, it produces like anywhere from 2 to maybe 10%. Some cases you might get up to even 30%, but that's very rare. So 2 to 10% partial melt will produce a less mafic magma. In other words, you're producing a mafic magma in this case, right? So 10% partial melt of peridotite produces basaltic magma, right? So that's why peridotite is so important. It partially melts to make these lavas that we see today, right? The basalt. Again, we don't see the ultramafic lavas, and they have a special name. Those lavas are called komatiites, right? So we only see komatiites that erupted about over 2.5 billion years ago during the Archean eon. So Earth did have a higher heat flow back then, and we could get 100% melted peridotite. So there are lavas called komatiites that date back to that time. But again, we don't see them anymore because Earth is not that hot anymore. Another important aspect of identifying igneous rocks, especially for the plutonic rocks, right? Remember, we're going to have the volcanic rocks that erupt from a volcano, and plutonic rocks that cool within Earth, right? So remember, Pluto is the Roman god of the underworld, so he's down below, right? So that's where these magmas are solidifying, and they're making granitic rocks, right? They're making this granite, diorite, gabbro, and obviously peridotites down below, right? So one thing we look at, since these magmas had a chance to completely solidify because they're cooling very slowly, they're insulated at depth, the minerals are growing. Some of these magmas take 200,000 to 500,000 years to completely solidify and crystallize, right? So the minerals grow large so we can see them. That's what we call it, phaneritic. Remember, phan means visible. And so we see these coarse grained rocks here, right? And so because the entire magma is solidified, we can use something called rock color here. In fact, what I call it mafic color index, or MCI. And what that stands for, it's really the percent of dark minerals, percent of those mafic minerals, right? So you can see that granites have very little, 0 to 25%. Diorites can have up to about 45%. Gabbros, 45 to 85%, and obviously the ultramafic rocks are going to be above that. And really the common mineral that defines a peridotite is olivine, right? So that's the main one that we'll look at here. In fact, one of our rocks to identify is a peridotite. So olivine is a key mineral in that rock. So in other words, for the color index, we're using the percent dark crystals. Like, for example, this picture of a granitic rock here, note that because there's lots of feldspar, lots of potassium feldspar, and that's what this has here. And there's some quartz, that kind of that light-colored, kind of vitreous mineral in there. Well, if I kind of take all these dark minerals and put them off to side here, it's maybe 20% of the rock, not quite 25%, 20, let's call it 22%. And so that would fit in the granite. So I can call that a granite, right? If we go back to, we had this picture here, you can see there are a lot more dark minerals here. So I would say like at least 40% of this rock is mafic. So 40%, that would make rock E there a diorite, right? So let's look at it. So diorites, yeah, that would be in here. So that's how we can identify these plutonic rocks, by using the mafic color index. For volcanic rocks, we got to use something else. Because volcanic rocks, not all of the magma solidified. So we don't know what minerals would have manifested if this matrix would have made minerals. We don't know because the lava cooled too fast. So remember, lavas are fast cooling. So for volcanic rocks, I think I have a diagram down over here. Here we go. So instead of using mafic color index, we're going to use the color of the matrix, right? So if the matrix, that cookie dough, white, pink, or red, it's usually some sort of felsic rock, which is going to be a rhyolite or a dacite. If it's green or gray color, the matrix, then it's intermediate. It would be some sort of andesite. And obviously if it's black, or if it's a red cinder, that's scoria, then we call it a basalt, right? So if we come back up here and look at our table up here, so this porphyritic rock, because I see a dark matrix, it's probably a basalt, right? And I would guess basalts should have some pyroxene and olivine in them here, right? Yeah, olivine here, accessory minerals, right? So basalts usually do have olivine. In fact, one of our samples has little olivine phenocryst, and it is olivine basalt. In fact, we would call it an olivine basalt. So your job here is to identify these samples, right? So which ones have felsic compositions, which ones have mafic. So the pink, so in this case, this is fine grain, so I cannot use color index, so I have to use matrix color. It's pink, so that's probably a felsic rock. Well, rhyolite's felsic. Gabbro, that's about 85% dark minerals, that's definitely a mafic rock. So here's a gray matrix, so figure that one out, right? So anyways, that's what you want to do for those samples there. They make it easy. They've given you the names of the rocks there already, right? So, but nonetheless, you can use this figure 211 as a guide to help you identify the rocks that we're going to look at later on, right? For the big part of this lab, identifying those rocks. And so that's where 2.4 comes in. So now we're going to identify the rocks, and you can see I want you to look at samples A through R, and I've already given you some hints as to what the rocks, whether they're phaneritic or aphanitic, or maybe vesicular or glassy, right? And I've given you, some of the minerals that are present, and then your job would be to I guess I didn't fill out here, so we'll have to look at what sample D is. In fact, we'll do sample D just because I missed this spot right here. But then where you see the boxes, you're going to have to enter the data there, right? So let's look at the first set of minerals here, or first set of rocks here. So we'll go back to our Canvas page here, and we'll look at the igneous rock. So you want to click on this link here. Remember, we're doing A, B, D, E, and F. So we're not doing all of them that you'll see. So note that we're skipping C here. So let's go over here. In fact, we'll do A first, and then we'll do D, because I'm going to do that with you. So we'll go over here, click on the link. And so you can expand this. So this is sample A here. We'll expand sample A, and you can zoom in on it. And right away, I see, if I can move this over, there it is. I can see the green olivine. Look at the vitreous green olivine crystals, right? So, and note that it's slightly vesicular, right? So green olivine, and so those would be the phenocrysts. And then the black is the matrix. And you can see it's a black matrix with slightly vesicular. So if we go over to our sample here, we would say that sample A, it wants a composition, so it's going to be mafic. So let's put mafic there, right? And I've given you some of the minerals, olivine with a minor vesicular texture. And so because it has olivine, minor vesicular texture, we want to use that matrix color, right? Just to help us identify it. And as you can see here, so if it's mafic, it has that black matrix, so it's going to be, it has the olivine, it's going to be the basalt, right? So this case, in fact, let's just call it an olivine basalt. Olivine basalt. There we go. And then now for sample D, well, it's phaneritic. Let's take a look at sample D here. So we'll go down here to sample D. And you can remember, you can move this around here, right? So it looks, yeah, so I see lots of crystals in there. We'll expand this here. And let's zoom in a little bit here. Looks like they cut this sample here. And I see lots of kind of gray quartz, some gray quartz in here, some feldspar, maybe some biotite mica in here. So it has lots of this quartz here. So it's definitely going to be lighter colored. If I do the color index on here, this is probably like 5%, 10% dark minerals. So very low color index. So if we go back to our first sample D, what I'm going to add here, I'll add that it's going to be felsic, right? This is going to be felsic. And then in fact, I can add that in right now just so we can have it in here. Let's add that in here. So this rock is going to be felsic. And then let's add that it's a mafic color index of about maybe 5%, right? And that's going to help us identify that low color index is going to be felsic. So here we want to put felsic here, right? And then for that low color index, we're seeing it's felsic, right? So we're going to go over here, and we said it was about 5%, so that's definitely in the felsic. So that rock is a granite, right? So we'll just call sample D granite, right? And so that's what you want to do for the rest of the samples here. Take a look at the samples, and then you can complete the identification first, all the way to sample R there. All right, so now let's look at the sedimentary rocks. These pictures are very helpful to help you identify the samples that you're going to be available to you online there. And then for sedimentary rocks, remember there's two major groups. There's the detrital. Remember, I call these siliciclastic because they're mostly broken silicate minerals. Remember, classic is broken. And then there's the chemical or biochemical, right? So there's a variety of different sedimentary rocks in here. And then as we go through here, use the pictures here to answer these questions here. Then when we get to identifying sedimentary rocks, we have some data tables here. So one thing I want to say before we go on to sedimentary rock samples here is we're only skimming the surface here for sedimentary rocks, because remember, sedimentary rocks are recording Earth's history. In fact, I call them the archives of Earth's history. So later on, there's a whole lab, a whole week that we're going to spend on sedimentary rocks and sedimentary rock textures and structures like cross bedding and graded bedding and mud cracks and all those features we see and we can interpret to help us identify, or we can identify today and help us interpret the geologic past, right? So again, the table here, we have detrital, which are the siliciclastic sedimentary rocks. Remember, they're composed mostly of broken quartz, feldspar, olivine, pyroxene, all the silicates. And then the chemical ones that either precipitate out of water or, well, obviously most of them are precipitating out of water, or they're being formed by some sort of organism that later dies and leaves behind a shell or leaves behind its skeleton, and those make a different type of biochemical sedimentary rock, right? So again, we have some samples that we're going to identify here. So let's go down here and look at our table. So same idea here. So in this case, the texture, either it's mud size, sand size, or gravel size. So that's all you have to put down here for the size. And then for the rounding or sorting, so by looking at the grains, how well rounded are they? Are they angular? Are they poorly sorted, right? So you want to put that in here. And then obviously I've done this for you already, so that kind of helps you. So if the word says siliciclastic, then we're definitely looking at the detrital column here, right? If it says chemical, right, yeah, then you want to use the other one there, right? So looks like most of these rocks I picked are siliciclastic. We only have the one chemical right in here. But nonetheless, that's going to be a sort of a guide to help us identify these rocks here. Then you give their name here. So let's look at the first one here. So we'll go back to our rocks here. And so sedimentary rock samples, we'll do sample A. Oh, sample A. In fact, sample A and B kind of go together. And you can see that they're both composed of gravel size. So remember the scale here. So anything larger than 2 millimeters is gravel, right? So these are are way bigger than 2 millimeters. So they're gravel size. But sample B has it's poorly sorted. It's different sizes, and so is sample A. Poorly sorted. They're different sizes. So both of these are poorly sorted, which means we would call this an immature rock. In other words, the sediment was eroded, weathered from some mountain, and then is starting to go down the river, but it hasn't gone very far. It's still up in near the headwaters, right? Because the sediment hasn't been worked, hasn't been separated coarse from fine, right? So it's still considered immature. And the breccia is angular, whereas well, I guess I told you what this rock is, breccia, whereas this rock is more rounded, right? So when you look at our charts here, right, so we'll go back to our lab, you can see that there's two fundamental rocks there. One that are gravel size. You're either going to have the conglomerate or the breccia, right? So actually the samples, the first two samples here that I'm asking you to do for this activity, A and B, are easy, right? So I'll let you figure those out. And then just follow the same line of thinking to finish off all the way through R, right? But remember, for siliciclastic rocks, you want to place here whether it's round or angular and the degree of sorting, right? So remember, both A and B were poorly sorted, but they differed in their rounding, right? So again, we're going to do a lot more sedimentary rocks, right, as we go on. In fact, one of the things we also will be doing in more detail is this environments of deposition, right? And so rock gypsum, that's a mineral gypsum that usually forms in arid or environments that are drying. So that's more of a desert environment where there's evaporation. So you can look at the chart down here to figure that out. So that'd be some sort of, not a swamp, but some, like over here, some little sort of salt flat or something. In fact, there's gypsum that's forming in the playas, the dry lake beds of Death Valley in the California deserts there. Conglomerate, right? So the big rounded boulders have to be in some river, right? Some river channel. You need the energy of water to move this stuff, tumble the broken fragments, the clasts, and to make them more rounded. Sandstone, if I asked you to go find me some sand, you'd probably go to the beach. So that's a shoreline environment. Shale would be somewhere finer grain, it's mud size, so that's somewhere offshore, but not very deep water, still near the continent, so maybe the continental shelf. Coal, well, coal, you need plants, some sort of swamp like they have down in here, right? And then travertine is usually formed at hot springs, or in fact, if you've ever been out to Alum Rock Park here in San Jose, those warm springs have a bunch of travertine on them. So you have to have some sort of percolating water, usually warm water that's moving calcium and carbonate around to produce the travertine. So anyways, you can answer those questions by kind of looking at these different environments of deposition here. Other things we also look at are sedimentary structures, and this is a classic structure right here where we have these cross beddings. These are aeolian dunes. Aeolian means wind blown, and usually the aeolian dunes are very large sets, and these cross beds are called foresets. And so if they're bigger than about a foot, they're wind blown, right? And these are clearly like, maybe 20, 30 feet tall, right? They're giant sand dunes. This is over in Zion, Zion National Park. And remember, so just kind of read through this and you'll kind of get an idea of the cross bedding. We'll talk much more about cross bedding later on in the semester. And then metamorphic rocks. Again, same idea. We got the table, right? For metamorphic rocks, we're looking at either foliated rocks or non-foliated rocks, right? Remember, meta means change. Meta is a change part. Morph is shape. So meta, change, morph, shape, right? So that's what the word means. And you can see that foliated rocks are going to have some preferred direction, either some slaty cleavage. So slate is very fine grain. It's usually, very fine. I always call it mud size, right? And it's going to have this very flat foliation. In fact, slate was used for chalkboards because it was very flat, and also for the really nice pool or billiard tables, right, for playing pool, because it's heavy and it's flat, right? So the ball will roll true on a slate table there, right? Phyllite is also mud sized, but note that it has a slight wavy foliation, and usually slite has usually phyllite has a sheen, a gloss, yeah, glossy sheen to it, right? So that can, and because often it looks like slate, but it has that glossy sheen because the metamorphic grade or the temperature of metamorphism is slightly higher. In fact, that's another thing this diagram is showing for foliated rocks. As you go from slate down here to gneiss, the temperature of metamorphism or the grade of metamorphism increases, higher metamorphic grade as you go toward gneiss, right? And so the difference between schist and gneiss is schist is a mineral foliation, a schistosity. So the minerals, the long axes of the minerals or the flat surfaces of micas are all aligned, giving that foliation, right? Whereas for gneiss, there's a definite dark banding and light banding, so a definite banding in the rock, right? So clear segregation of dark and light minerals, right? Whereas micas dominate, yeah, so the scaly foliation, they call it the schist over here, because the minerals define the foliation for this schist, but the banding defines the foliation for the gneiss. And then for non-foliated rocks, right, you can see there's marble, quartzite, metaconglomerate. In this case, it's a stretched metaconglomerate. Andesite is a type of coal, right? Hornfels is kind of a rock that's been burned by contact metamorphism. It could be just about any type of rock that's just been burned, right? And then serpentine. In fact, that's important. There's lots of serpentine or serpentinite in California. Serpentinite is actually the California state rock, right? Right? And that rock has a protolith. So does this have, yeah, the parent rock is what I call the protolith. So protolith means what the rock was before it was metamorphosed, right? So serpentinite often is, you know, a gabbro or usually a gabbro or a peridotite, right? So a mantle rock. So that's why serpentinite is kind of important. There's some mantle tectonics going on here in California, of which we'll learn about quite a bit in this class later on in the semester, right? So those are some, this is the key for identifying the metamorphic rocks. Then you'll go down here and the same idea, you'll take a look at the metamorphic rocks and then you'll fill out this data table here. So we'll look at the first rock here. So again, we're doing samples B, G, and so we'll look at sample B being the, and for sample B, in fact, sample A, you could tell that's a schist or a phyllite, had that sheen, see that sheen? But sample, in fact, this one also has that sheen. It could be a phyllite, but it has these bigger clasts, right? So these could be micas in here. In fact, let's zoom in on this one and take a look. Yeah, so these are garnets. So they look like little soccer balls there, right? You see one's popped out there. But that shiny foliation, that's definitely a foliated rock, and it has lots of white mica and the garnet in there, right? So what do I say about this sample here? Foliated, right? And the grain size, so let's say it's sand mica, and then large garnet. And there's a special name we use for the large garnet. We call that a porphyroblast, right? So porphyroblast, just like porphyritic in igneous in metamorphic rocks, we use the word blast for, because it's grown from the metamorphic processes, right? It's grown in the plane of foliation, right? So fine, and so you can call this rock a garnet schist. So we're using the adjective garnet here to emphasize that it has these big porphyroblasts of garnet, right? You can see I've filled out quite a bit for you already. Go ahead and start looking at these rocks, and then you can fill out this data table here. And that's it for this week. All right, guys. See you next time.